Hello and welcome to Tutorial 5 for Applied Science 179. Today we will be going over Module 4, or a bunch of the material from Module 4. We'll be talking about transformations and then coordinate frame transformations. So, our first question is, using standard coordinates and transformation of the standard basis method that we learned in Module 4, create a transform that will scale the z-axis by a factor of 2 and mirror the x and y-axis, or axes, sorry, make them just -1 times their current value. Okay, so if you'll remember, in this method we take the standard basis, which is just essentially an identity, and we take each one of its columns and we apply the set of rules that our transformation is trying to make happen to those vectors, put them back together into a matrix we call A, and that matrix will then be the transformation matrix. So we can just multiply vectors by A and it will do this transformation for us. So generally with these ones, the best thing to do is just to write out the rules. I find that very helpful, so let's take a quick look at that. So what were the rules as far as this transformation was concerned? So we want to create a transform that will scale the z-axis by a factor of 2. Okay, so we could just write that down. So each time we do this, we should have 2 times, well, actually, let's use a dot for that. 2 times z. So we'll write it that way so we don't confuse multiplication with x. Okay, so that was that first rule. So scale z by a factor of 2 and mirror the x and y axes. Make them -1 times. Okay, so we should have minus x and minus y. Okay, so those are our 3 rules that we will be applying to each one of those basis vectors. So let's start with our first one. Okay, so we do the transformation on S1, and S1 is what? It is the x-axis. Okay, so it's the first column of an identity matrix. And if we apply our set of rules there, what do we get? We should get minus whatever the x value is, so we should get -1, minus the y value, so -0 is just 0, and 2 times the z value, which is again just 0. So we should end up with -1, 0, 0. Okay, so let's try that with our next one. So our second vector here is going to be what? It is the y vector, the second column of an identity matrix. That is a 0, not a 6. Okay, so let's apply our set of rules here, and what do we get? We get minus x times 0, so -0 is just 0. We get minus y, so -1, and 2 times z, 2 times 0 is just 0. Okay, so we have the second column of our matrix figured out, and we perform our set of rules on now the third column. So this was S3. So that was S3. Okay, and so that's the third column of our identity matrix, so 0, 0, 1. And if we apply this set of rules, we get -0 is 0, -0 is 0, and 2 times z would be 2 times 1 is 2. Okay, so now we have those 3. We're ready to assemble them, just as is shown right over here. So we can assemble those into A, and so what does A equal? A is going to equal -1, 0, 0, 0, -1, 0, and the third column is 0, 0, 2. Okay, so there we go. We could multiply some vector by that. Let's multiply the vector 1, 1, 1 and see what we end up with. And we should basically get our rules back. So we have -1, 0, 0, 0, -1, 0, and 0, 0, 2. Multiply by 1, 1, 1, and see what we get. We will get 1 times -1 is -1, plus 0 plus 0, 0 plus negative 1 plus 0, and 0 plus 0 plus 2. Okay, so essentially we just got our rules back, and that one checks out. Looks like it did what it was supposed to do. Okay, so if it's not one of the standard transformations, you can either build it from a bunch of other transformations, or you can use this standard basis method where you just apply your set of rules to the standard basis, and you will end up with your transformation matrix. Okay, question 2. You can represent a triangle as a list of their 3 vertexes. So we have a triangle here, it has 3 vertexes. So all we need to do is move those 3 points, and we have moved the triangle, because we can just connect up those points and we have our triangle back. Okay, so, and in fact, most computer graphics, at least in video games and things, are moving around little triangles. And a lot of the math actually has to do with little triangles. But let's keep going here. So, develop a sequence of transforms that will allow you to transform triangle 1 to triangle 2. So we want to be able to take triangle 1 and we want it to end up where triangle 2 is. Make a sequence into one combined transform and use homogeneous coordinates. Okay, we better start actually using homogeneous coordinates all the way back in step A, because there's actually a transformation, or a translation, sorry, that is a part of this transformation. And so we are going to have to use homogeneous coordinates, otherwise translation is not available to us. Okay, so how will we do that? So let's figure out what we want to do with this thing first. One of the easiest ways is to move it to the origin, and then we would have something that looked like that. We would then want to say we could mirror it across the y-axis here, so basically set the x-axis to negative value, that would put it there, and then move that point up to there. So we could do it in those 3 steps, or you could mirror it across the y-axis to start, and that would get you something that looked like that, and then move it from there up. You can do that. If you were doing it generally, you'd probably do it that first way, just because you know from where it is to the origin, and you know where you want that point to end up, at least in theory, so it's a little bit easier to do those calculations straightforward, and the one set of geometry doesn't need to know where the other set is, although it's probably not all that hard to do that calculation directly anyway. But either way, we can set this together. So let's do the first version we had there. So the first thing that we were going to do was what? We could translate to the origin. Okay, so translate by what? -1, -1. Okay, so if we translated -1, -1, that would put that point back there. And then mirror, we could say mirror x, which is mirroring across y. And then our last version was the translation back up there, and so that was translation of -2 and +3. Okay, so those are those 3. Now you'll notice I wrote them from right to left. We started, that was the first thing, first, last. Okay, and that's because when I write the vector, or the points, they will go over here. The first thing they get multiplied by is the one furthest to the right, then they get multiplied by mirror x, then by the translation matrix. Order, of course, matters, and if you change that up, it will, of course, change up your answer. Please do make use of the MATLAB scripts that I've given you. You can make up your own set of triangles, just put 3 points and have it draw a line between those 3 points. Okay, and that would allow you to apply all the transformations you wanted, and you can see it move around and just replot it. Okay, so make use of that MATLAB script, give you a chance to really intuitively play with it and get a feel for it. And it can even be fun. Okay, so here we go. We got our translation, mirroring, and then another translation. So let's write those matrices out. And what do we have? We're only dealing in x and y, so we can work with x, y, h. We don't really need to keep z in there, so let's do the slightly smaller matrices for that. Okay, so our translation, -1, -1, so a translation matrix is going to look like a little identity on that side, and the last column will hold the translations, so -1, -1, and you can get that off of our set of standard operators. Okay, so mirror x, we are going to mirror across the y-axis, so we've got 1, 0, 0, 0. Well, I've already messed that up. It should be -1 for x, because it's going to mirror across the y, so positive x values are going to become negative x values. And for our y, it is not changing, and then we just have h sitting over there. Okay, and our last one that we have is going to be another translation matrix, and so it looks like a little identity with some stuff in the last column. Again, our standard operators list, I'm going to give that to you on the final exam. You don't have to memorize the standard operators. You'll start to get used to most of them because there's a few of them that you use more than others. Okay, and so our final one is our x value is going to be -2, and we're moving 3 in the y. Okay, so that is our set of 3 matrices, and our second one is make the sequence into one combined transform. Now again, we can multiply these all together. It will get one matrix left over. That matrix will do all 3 of these operators at once and move things directly from 1 all the way to 2. Okay, so let's multiply those together. Let's multiply the first 2 here. What do we get? We get -1, 0, 0, 0, 1, 0, and -2, 3, 1. And that is a 0 there. And this one, of course, stayed the same. This 1 and 1. Okay, and then we'll multiply this last set together here, and what do we get? We get -1, 0, 0, 0, 1, 0, and we get 1, -2 is -1, and -1 plus 3 is 2. And our last one here will just be 1. Okay, so that is the transform that will take us from 1 to 2. You'll notice it basically flips the x values, right? That's what you're seeing here. It's going to flip our x values to be negative and translate -1 in x and +2 in y. Okay, so even though we did this by building it by going to the origin, mirroring across the y-axis, and then moving it back up, okay, even though we built it with 3 of those, okay, we can see in here that we could have just mirrored across the origin and moved up, back 1, up 2, right? So that would take us back to that spot there. So either way we did it, we would end up with the exact same matrix because that's the matrix that does that action. However, we could get to it many different ways. So we could apply all sorts of different transforms. We could have first moved it up to here, then moved it down to here, moved it over here, mirrored it back over here, mirrored it over there. We could have done all sorts of things. So long as that sequence of transformations moved it from 1 to 2, when we multiplied all those steps together to get one transform, we would still get this exact same transform. Okay, it's sort of like if you were doing Gauss-Jordan, you know, you could do all sorts of silly maneuvers that are not part of the algorithm. So long as you keep following the rules, you're not going to break the answer, and you'd still always get the same reduced row echelon value. So same sort of concept. You can do all the transformations you want, but once you have actually multiplied them all together, there is only one answer down here. Okay, so it's that simple. We will now move on to actually show it with moving the points. Okay, so the points of that triangle, the original triangle, were what? They were, unfortunately you can't see it, but they were 1, 1, 1, 4, and 3, 1. Okay, so that's 1, 1, 4, 1, or sorry, 1, 4, which was up here, and then 3, 1, which is over here. Okay, so there's our little triangle and our 3 points. If we have them in homogeneous coordinates, that would be 1, 1, 1, 1, 4, 1, and 3, 1, 1. Because remember, h is always going to be 1, and our coordinate is, of course, x, y, h in homogeneous, and h is always 1. At least when we're not dealing with perspectives. For the purposes of our course, we always pick h as 1. Okay, so we had our set of those matrices, we had multiplied them together and combined them, and we had already done that on the last page. And what had we come up with? We had come up with minus 1 we had come up with minus 1, 1, 0, 0, 0, 0, and minus 1, 2, 0. Sorry, whoa, definitely not 0 down there. It should be a 1. Always a 1 down there, because that's going to keep our h from changing. Okay, so we have our combined matrix. So if we multiply a by h, okay, so we should have minus 1, 0, 0, 0, 1, 0, minus 1, 2, 1. And our points, let's multiply them by this. So what do we get? We have 1, 1, 1, 1, 4, 1, 3, 1, 1. And the multiplication gives us what? So we should end up with, in our first column, we have minus 1 plus negative 1, so we have minus 2. And next row we get 1 plus 2 is 3. And our last row we get a 1. Okay, second row, or second column, so 1, 4, 1. And that gets us what? That gets us minus 1, or minus 1, minus 1, so minus 2. And second row we get 4 plus 2 is 6. And our last one there should be a 1. Okay, and the last one, so 3, 1, 1, multiplied by that, we get minus 3, minus 1, so minus 4. And 1 plus 2 is 3. And of course a 1 on the bottom there. Okay, so those are 3 new points, which if we had this thing sitting here, we had minus 2x plus 3, which was sort of there-ish. We had minus 2, y is 6, so up here. And we had minus 4 and 3, which is, of course, about there. And there is our little triangle. Okay, so we can move the geometry from one place to the other with these nice transformations. We can build them up from a bunch of simple operators and end up with complicated operators that can move points from one place to another. We could have added rotations, we could have added scaling, we could have added any sort of transformation that we wanted, and that allows us to move these things around. Of course, we've worked in homogeneous coordinates, which allowed us to do translation, and this is essentially how you move things around in computer graphics, or if you've ever done any kind of drawing, I'm sure you moved stuff around on the screen and you mirrored it and did all sorts of wonderful things, and that is just a bunch of these different transformations being applied in the background. You don't get to see it, but computers are wonderful at just churning through these numbers. So that's what is sitting behind all of that. Here's that all in a slightly prettier format if you can't read my handwriting, which is always very possible. On to question 3. So the question asks, find the transformation to convert between the coordinate frames of the airplane and balloon to the tower's coordinate frame in the drawing below. Okay, so we want to go from the plane to the tower and from the balloon to the tower. Okay, so we're going to move coordinates from those two perspectives to the tower's perspective because he's trying to figure out where the plane and the balloon are. Okay, so let's first off look at our plane. So the first thing to do is we will start with our bottom row here, which we know is going to be 0, 0, 0, 1 because we're working in homogeneous coordinates. Okay, now we want to find the origin of the plane, okay, with respect to the tower's coordinate system. So for this, if you need to, you can think of there being no little arrows here, okay? Or no, yeah, just forget about the arrows for the moment. Okay, so I've made you forget about the arrows, hopefully. Okay, all we're really worried about at this moment is this one point right here. Okay, this point is all we care about. Where is that point with respect to the tower? Okay, so it is where? It is in the tower's x-coordinate, 10 kilometers. We'll do all of our units in kilometers here so we don't have to try and write units. In the tower's y-axis, it is 13 kilometers. And in the tower's z-axis, it is 2 kilometers up. Okay. So that's where our airplane is sitting. Actually, I have no idea if those are reasonable numbers for the altitude of a plane. But anyways, this plane is at 2 kilometers up. Okay, so we found the point, or the plane's origin from the tower's coordinate system. Now that we've done that, we should be able to bring back our arrows here. Okay, so that we're ready to start dealing with orientation. Okay, so we've done this part. So that's the quick and easy part, and now we need to line up the origins and look at their orientations. So we have Z from our tower, okay, and it's X. So X from the tower is going that way. Y from the tower is going that way. So if we were to lay the origin of the plane at the same origin as the tower, what would we get? Our two z's are equal, so the z direction from the plane is pointed that way. The x direction from the plane is pointed that way. And the y direction from the plane is pointed in the same direction as x. So we can pick those, or we can put in these values. So the x of p, so the x-axis of the plane from the tower's coordinate system will be what? The plane's x is 0 in its x, minus 1 in the y, and 0 in the x. Or sorry, 0 in the z. Okay, the y-axis of the plane from the tower's perspective is in its x direction, and the two z's match. Okay, so if you were to look at that, you would see that this is actually a rotation by 270 degrees around the around the z axis, right? So that's going to be sine of theta equals -1. So if you go back to your rotation around z is cos theta minus sine theta, cos theta, and 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0. Okay, so that's rotation around z. And in this case, we rotated around z by 270 degrees to go from the tower's perspective to the plane's perspective. And so that's where those numbers come from, or you can just think about it as the basis vectors for the plane from the tower's coordinate system when their origins are on top of each other. Okay, so hopefully this is working for you, and this is all reasonably straightforward. Okay, so let's do our next one. So the balloon. Again, we should be able to just do in our bottom row here. Okay, and so now we want the origin of the balloon from the tower's coordinate system. And so we have 7 in the tower's x, we have -4 in the tower's y, and 3 in the tower's z direction. Okay, so that was 7, 4, 3. Okay, so that would be the origin of the balloon from the tower's coordinates position, or the tower's perspective. And now we need to put their two origins on top of each other and find orientation. Okay, so what do we have? We've got, well, I don't even particularly need to write it out. We have z of the tower is equal to z of the balloon. Y of the tower is equal to y of the balloon, and x of the tower is equal to x of the balloon. Okay, so it's just going to be a little identity. They are the same. Right? So x of the balloon's x-axis in tower coordinates is just 1 in the x because they're sitting on top of each other. So we get a little identity. They are the same. Nothing's going to change with that. Okay, so we've found our two transformations. We can now move the plane's coordinates into the tower's coordinates, and we can move balloon coordinates into tower coordinates. So the plane could say, I plan to be 5 kilometers in front of myself in 15 minutes. It's probably flying faster than that, but anyways, it's going to be 5 kilometers forward in 30 seconds, say. And so, you know, is everything safe there? The tower can then convert those coordinates to its own coordinates and say, yeah, there's nothing in my space over there. Okay, so they could do that. However, at this point, the balloon is just getting a little antsy and wants to know where the plane is. Okay, so there are those numbers in prettier format so that you can read them. And on we go. Okay, so again, we've got our two transformations. They're letting us move plane to tower and balloon to tower. The people in the balloon, they're feeling a little bit antsy about where that plane is, and they want to be able to convert plane coordinates into their own coordinate system. So what do they need? They need a transformation, okay, that will take them from plane coordinates into balloon coordinates. Okay, but what I have is, I have plane to tower, and I have balloon to tower. Okay, but those two things don't cancel out. This doesn't work. Okay, so what do I really need? I need something that will allow me to go from plane to tower, and then tower to balloon coordinates, because then those two will cancel out, and I will end up with my transformation that takes me from plane coordinates to balloon coordinates. Sorry, I'm swapping between big B's and little b's here, but they should hopefully be the only b's in here. Okay, so that's what we need. So we don't currently have a transformation that takes us from t to b. All we have is a transformation that takes us from b to t. Okay, so we need a transformation that's going to go the opposite way, and in this case all we need to do is find the inverse. Okay, if we can find the inverse of the transformation that takes us from t to b, we will get b to t. Hopefully that seems straightforward and logical. It's just going to be able to perform the steps in the opposite direction. So if we want to move coordinates in the opposite direction, we just need the inverse of the transform that takes them in the first direction. Okay, so let's do that. Let's find the inverse. The easiest thing to do with this is just going to be our sort of good old Gauss-Jordan. So let's put the transform t to b right here, which was 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, and 7 minus 4, 3. We'll augment that with an identity. Okay, and so we need to get our left-hand side to look, or the left-hand side of that matrix to look like an identity, so what do we need to do? Let us go minus 3r4 plus 4r4 and minus 7r4. Okay, so if we were to do that, what would we end up with? We'd end up with an identity sitting over there, and on this side we will end up with 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and minus 7 plus 4 minus 3 and 1. So in this case, we're only actually having to flip the sign. Now, if there had been some orientation differences, there'd be some slightly more interesting things that would be happening there. However, this one was super simple. Of course, that's the way I planned it, just to make my life easier. However, it wouldn't have had to have been that way, but we would still find the inverse in the exact same fashion. Okay, so we would just do it. It's just that this Gauss-Jordan would take us a few more steps to get the identity on the left part. Okay, so over here we have our transformation. Well, let's just write it up here, which is 1, 1, 1, 1, 0, 0, 0, 0. Lots of zeros, minus 7, 4, minus 3. Okay, so that's the transformation that we were looking for. We should be able to now multiply these together and get the transformation that takes us from the plane to the balloon's perspective. Okay, so t from the plane's perspective to the balloon's perspective is the multiplication of these two matrices. So what do we need? We need the tower to balloon and 0, 0, 1, 0, minus 7, 4, minus 3, 1. Okay, and we'll multiply that by the plane to the tower, which was 0, minus 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and 10, 13, 2, and 1. Okay, so when I start multiplying vectors on this side over here, it's going to get taken, so I can take coordinates, if I put a coordinate here, from the plane's perspective, this matrix will move it to the tower's perspective, and then this one will take it from the tower's perspective and move it to the balloon's perspective. So I would have moved a vector that was in the plane's perspective all the way to the balloon's perspective. Okay, so let's multiply those two together so we can have a combined transform. And what will we get? We will get 0, negative 1, 0, 0. And our next one will be 1, 0, 0, 0. Third one, 0, 0, 1, 0. And our last one is where things start to get ever so slightly more interesting here. And what do we have? We have 10 minus 7 is 3. We have 13 plus 4 is 17. And we have 2 minus 3 is minus 1. Okay, and of course 1 for our homogeneous coordinate down here. Okay, so there is our transformation that will take coordinates from our plane's perspective to our balloon's perspective. We could multiply that. Okay, so let's just do like that and pretend like we're doing the multiplication by a vector now. So we could take something from the plane's coordinate, say the origin of the plane, so that the people in the balloon would know where the plane is. We can multiply those two together, and what would we get? We would get 3, 17, minus 1, 1. Okay, and so if we were to go back to the picture, and by all means rewind this thing at this point, I unfortunately can't rewind. Oh, but I could go for it. Hold on. There's that in pretty format. And here we are back to our picture. Okay, so let me redo that one. So if we were trying to take the origin of the plane here, do the multiplication, we get 3, 17, minus 1, 1. Okay, so from the balloon's perspective, the plane is at 3 in its x, 17 in its y, and 1, or negative 1 in its z, which if you look at it, they are, it's a kilometer below it, so that makes sense. Minus 1, 17 away, so we have 13 plus 4 is the 17, and we have 3 different in the x-axis, which is of course the difference between the two. So that actually makes a lot of sense. If we were to look back up at the diagram, we would be able to pick those numbers out pretty easily. And if we wanted to say take this, the perspective of the plane, if it was to move forward 5 kilometers, so the plane is going to fly forward by 5 kilometers. Where is it going to be now? We just have to multiply the plane's perspective, 5 kilometers in front of it. So in 30 seconds, say it's going to be 5 kilometers farther forward. Is that going to be interfering with the balloon? I don't know. The balloon's a little worried about it. Let's check it out. So if we multiply those two vectors, what do we get? We get 5 times 0, 0 times 1, 0 times 0, and 3 times 1 is 3. Okay, and then we get minus 5 plus 0 plus 0 plus 17, so that would be 12. And then we end up with minus 1 and 1 for a homogeneous coordinate. Okay, so in that case, the balloon knows that it's actually still pretty far away. It's 3 kilometers in the balloon's x, 12 in its y direction, and still 1 kilometer below it. So the balloon people don't have to be worried. They know the answer. They know where the plane is and where it's going, and they know it's not going to interfere with them. Okay, of course, it's still a pretty simple toy problem, but this can then become way more complicated. So this is what's used in CAD/CAM systems to have sketches and then parts, and then put those parts into an assembly. Each one of those different things has its own coordinate system. How do you draw them all once you've put it all together? Well, it's exactly this. It's those transformations are built for each one of those different things, and you just move those coordinate systems around and move the points from one into another, and you can see where they should be with respect to each other. Okay, so this is the math that is sitting behind all of those CAD/CAM systems and computer graphics, and it is exceptionally useful. It's used in GIS systems, which is geographical information systems. So if you're more into civil engineering, that's the sort of thing that you would be using this math for. It's what's running 3D printers, telling the 3D printer where it's supposed to go. It does a bunch of transforms and things. Yeah, it's math that's sitting behind a whole lot of things. It turns out to be super useful. I must say that when I did my undergrad, I didn't see the point, and then later on realized how incredibly useful it was as I had to use it in various things that I was doing. So it's wonderful stuff. I hope you're enjoying it, and that will be the end of our tutorial.